how many of you know what a matrix is? Right. And how many of you have ever heard the word pivot element? Ever heard that? That may be something you haven't heard or pivot column. So what we're going to do today at the beginning is we're going to do a little bit of morphology of matrices, right? So we saw last time that we can take a system of linear equations and basically write it in a matrix form, and it's easier to manipulate. And by the way, the more complicated your collection of equations are, the easier proportion the matrix makes. So a matrix is an n by n array of numbers. This could be real numbers or complex numbers, or something else. So, for example, something like this. That is a matrix. We would call this a 2 by 3. The 2 means there are 2 rows, and the 3 means there are 3 columns. Okay. The leading in each row and actually, let me and any non-zero. What do I mean by a non-zero? I mean a row that has something other than 0 in it. For example, this row right here, 0, 4, 0, is a non-zero row because it's got something in it that's not 0. The leading entry in any non-zero row of a matrix is first. Well, let me say it's leftmost. So the leading entry in the first row of this matrix is this, because 2 is the first thing that I come to that's not 0, and the leading entry in this row is 0. And of course, if you have a row of all zeros, there's no leading entry because nothing in it is not 0. Everybody clear on those definitions? Okay. Now, it turns out that if I walk up to you on the street and give you a matrix like this, we can always reduce it to a very convenient form. We will see this kind of reduction happen over and over in this class. Even as we start working with matrices in a more sophisticated point of view, this form that I'm going to talk about is very, very fundamental. And we're going to spend today talking about this form and showing how we can apply it to actually solve linear systems of linear equations. So what this is called is the and reduce this in parentheses because I'm going to talk about just plain old echelon form and then a little bit more specific, reduced echelon. Okay. And M by N matrix, we call it M is in echelon form. Yeah. Here, M by N means it's got M rows and N columns. You're always regular matrices. Okay. It's in echelon form if all rows of all zeros, if any, occupy boxes. So that is to say, if we have rows of all zeros, they all have to be sitting at the bottom. Number two, each leading entry of a non-zero row, is in a column strictly to the right of the leading entry of the row above it. Okay, so I'm gonna do some examples and try to straighten it out. That's a lot of work, but it's kind of hard to picture that. But if you have a leading entry of a row, it has to be to the right of whatever the leading entry of the row is above it. This third thing here, I repeat this because your book does it, you're following the textbook, but it's actually redundant. It follows from what was before, but it's probably worth recording because it helps picture it fine. All entries in a column below a leading entry are zero. Okay, so this is what it means to be an echelon form. I haven't told you what it means to be reduced echelon form yet, but let me give you some examples. Let's just repeat this matrix here. Let's see what happens with this. Well, what are the leading entries of this matrix? Well, the first thing is all rows consisting all of zeros have to be at the bottom. Well, there aren't any rows consisting of all zeros, so we're good to go there. Everybody okay? Second point, each leading entry of a non-zero row, so there they are, is in a column strictly to the right of the leading entry of the row above it. Well, there's only one row with a row above it, and that's this row. And notice the leading entry is strictly to the right of the one. Okay, so that's good to go. Yes.
Does it have to be like the column directly over, or maybe like two over or three over?
Oh, you mean like the 4B here?
Yeah.
Certainly. Okay. Yeah, and I'll give you an example of that. And all entries in a column below any leading entry are zero. And notice, here we go, and there's nothing below this. So this one is actually an echelon form. As per the question here, does that address what you were curious about?
Yeah.
This one is also in echelon form, right? The rows of zeros are all at the bottom. They're located to the bottom. Your leading entries go down and to the right. Okay, so that's what it means for a matrix to be an echelon form. And in fact, I'm not going to prove this, but you can reduce, I think it will be kind of obvious from the computation you do, you can always reduce every matrix to an echelon form. Unfortunately, if I give you a matrix and you reduce it to echelon form and you reduce it to echelon form, chances are you're not going to get the same thing. They're going to look slightly different. However, if you use reduced echelon form, the answers you two get will be the same. So let's add to this. If, in addition, the matrix M satisfies number 4, leading entry in each non-zero row is 1. And each leading 1 is the only non-zero element of this column. If you have these two conditions here, then we say that M is in row reduced echelon. Which I will sometimes abbreviate RREF for row reduced echelon. Now, notice that these two matrices are in echelon form, but they're not in row reduced echelon form. Because first of all, the leading entries here are not ones. And in this case, and also when you look at where the leading entries are going to be, it's not in a column consisting only of that element. However, I can turn both of these into row reduced echelon form by doing this. So notice that, what did I do? I multiplied the top row by 1/2, and I multiplied the second row by 1/4, right? So now I've got leading entries 1. Everybody agree with that? And now I can use this 1 to nuke this. 1, 0, 1/2, 0, 1, 0. Right, because all I have to do is multiply that, a -3/2, kill that. And now this is in row reduced echelon. To fix this, notice I've got that 4, which is problematic. Three, 1. Oops. Yeah, that's right. That's right. So basically, all I did is multiply this by 1/4. Third row by 1/4. And then from here, I can use the 1 to take out the pair above it. So continuing my computation here, I can use this 1 to take out that 3, take out that 6. Right up here. So this is going to be 1/0, and this is going to be 0, 0, 0, 1, 0. And it's still not quite in row. Yes.
When you say take out, does that just mean you're following the rules, so it's just they get wiped?
Multiply that by -3 and add it to that. Right, that's one of our row operations. Multiply this by -6 and add it up here.
Okay.
And notice since all the other entries are 0, it doesn't mess with anything else.
Right.
So that makes sense. And notice that I did this first because now I'm gonna have to take this out, and I'd rather take that with all zeros than. So see, now this is much easier to take out. Multiply this by -2 to take out that 2, and I get 1, 0, 1, 0, 0, 0. This one is in row reduced echelon form. Leading entries move to the right. They're all 1s, and each leading entry is the only non-zero entry in its column. Everybody? Any questions? Yes.
So when you're like thinking the things that you're really multiplying the whole row by like negative perhaps, or whatever it is, let's see, consider it zero. Instead of doing that.
Yeah, that's right. That's exactly right. Okay. Here is a theorem that, like I said, I'm not going to prove this, but it's very important. And we will see why this is true, basically from row and column operations. So here is a big theorem, okay? Every M by N matrix. M, what's that? Is equivalent by a sequence of row operations to a matrix in row reduced, actually, so to a unique matrix in row reduced. So this theorem really, yes.
What does unique mean here?
I'm going to tell you that. This actually says two things. Number one, if I walk up to you and give you a matrix, you can do a sequence of row and column operations and get it into a form that's row reduced echelon form. What does unique mean? It means if I give you the matrix and you the matrix, and it's the same matrix, you will both end up with the same row reduced echelon form. All right. This is not true for echelon form. You might get different answers, but if it's row reduced, you'll get the same thing. That's what I mean by unique. There's only one answer. And let me give you an example, and we can sort of see as we go along how this works, I think. Suppose I give you the following matrix. Let me see. How about this? Suppose I give you this here, 210. 1 minus 1 minus 1, 3, 2, 4, and 0 minus 2 minus 1. And my instructions are find the row reduced. Now, I'm going to point out as we go along that there are different ways to come up with the echelon form, but the row reduced is unique. By the way, I know for a fact that I am going to get at least one row of all zeros. Does anybody know why? Yeah.
Because you need the height to be the same as or less than the width.
That's right. This one's got actually 4 rows and 3 columns, so it's going to actually turn out that you have to get a row of all zeros. And if you think about the pivot, or if you think about the leading entries, then that is sort of why this must turn out. So the first thing I'm going to do is, because I'm a lazy man, I'm going to use this 1 to take out everything around it. So in my matrix, I'm going to leave that the same. But what I'm going to do is I'm going to multiply this by -2 to take out this. That is going to give me a 0 times -2 and add, -2 and add, and that's what I get there. And I'm going to multiply this by -3 to take out that 3 there. -3, 5, -3, that's going to give us 7. And I'm going to leave this. Now, conveniently, I've got a 1 there. Now, my next step, one of my row operations, so what I used here is multiplying this by something and adding it to the others to sort of get rid of that, the entries in the first column. I'm also now allowed to rearrange my rows. So I'm going to rearrange my rows this way. One. I'm going to put that one on top, and I'll just relegate this down here. 0, 3, 2, 0, 5, 7, 0, 5, 2, 5, 7. Okay. And actually, you know what? I'm gonna make a change. I'm gonna swap these two rows too, because I can handle two better than that. I'm gonna go 0, -2, -5, and 0, 3, 2. Now, remember that I made that change, actually. Now, what I'm gonna do is I'm going to use this entry right here to nuke everything in this column, all right? So, in my next step, my second row is going to be the same. Let's see, how am I going to get rid of that? Well, I'm going to have to multiply this by -1/2 and add it, right? Because when I multiply that by -1/2, I get 1, and when I add it up there, 0. See, times -1/2, that's going to be 5 halves, minus 2 halves is 3 halves, like that. Now I'm going to use that -2 to take out this. So that multiplies this. So I'm going to multiply this by 5 halves and add it down here. And that's going to be 0, 0, the whole point. That's going to be -25 halves. And that's going to be 14 halves. And so it's -11 halves. Everybody okay? And now I'm going to have to take out that 3. I'm going to multiply that by 3 halves and add it. And that's going to be -15 halves, 4 halves. That's going to be -15 halves plus 4 halves. Very good. Everybody okay? Anybody see something easy I can do now? Notice I can use this row to do this one, right? Multiply this by -1 here. Guess what I got? A row of zeros. That's negative. Okay, let me point out something at this point, and that is this matrix is actually in echelon form. Everybody agree with that? Can somebody explain to me why echelon form could be different if you did the problem a different way? Anybody see? Yeah. That's right. See that -2 row? I just sort of picked it and used it to eliminate stuff. And so I've got a -2 here. Originally, I had the 0, 3, 2 here. If I had done it that way, which I certainly could have, I would have had a 3 here, which is a different matrix. Yes,
You swap columns or whatever like that as well.
not yet. We're only gonna swap rows at this point. Yeah, only rows. So let's move on to get row reduced echelon form. Here's what I'm going to do. I'm going to multiply this by -2 11s, and I'm going to multiply this row by -1/2. And this gets my leading entries to be 1, is all I. And now all I have to do is use this 1, use this row, this 1 here to take these 2 out. So I'll multiply this by -5 halves to eliminate that. Multiply this row by -3 halves and add it here to take that out. And I forgot my row of zeros. They're at the bottom. So here's my row reduced echelon form. And the amazing part of this theorem is the fact that you can get different echelon forms, but the row reduced echelon form, well, if you do it right, you'll all get the same answer. Okay. Any questions? Okay. So suppose I have an n matrix, call it, I'm going to define something. I mentioned this at the beginning of class called pivots. A pivot position is a position corresponding to a leading entry. In row. And that is leading entry position of this row reduce echelon form. That's where we put it. And a pivot column is a column containing okay, so for example, let's look back at our previous example. Notice this is in row reduced echelon form. I'm going to circle pivots. There are the three pivot positions right there. And these are the pivot columns. And this corresponds to the original matrix that we started off with. The pivot position just refers to the position in the outcome, right? So the pivot positions here, these are technically the pivot positions because they're the ones that positions there that result after you do the row reduced echelon form, and every column is a pivot column. Right? Here's another quick example of that. So for example, this matrix is not in row reduced echelon form, but can you all pick out where the pivots would be once you reduce it, even though we haven't reduced it? Which column should be the pivot columns? Yeah. Okay. That should be a pivot column, right? Because there'll be a leading entry there. In fact, it's already there. Right. This should be a pivot column because there'll be a leading entry there. This should be a pivot column. And this last one should be. Any questions? Yes.
Since row reduced echelon form is 8, can we go back from the reduced row echelon form to our original matrix?
No. In fact, there are many different matrices that will give you the same row reduced echelon form. For example, let me give you these. Both of these matrices have the same row reduced echelon. Right, so that's a good question because you always, any matrix goes to a unique row reduced echelon form, but once you have that row reduced echelon form, it could come from many different. Yes.
I thought you could just like reverse the elementary row operations.
Oh, well, so. But, yeah, you can reverse, it, but that doesn't mean, so, for example. This is in row reduced echelon, I agree. This one is not. Right. So, this could be the original matrix, or you could go backwards by reversing what you did, by taking this row and adding it to this row and getting this, right? So both this and this, even though they're different matrices, give the same row reduced echelon form. But there are many that go to it. Yes.
Is that in part because like with the bottom matrix there in that example, like using like 0 equals 1 to like do a lot of stuff above it. Right?
What's that?
But okay, so in the bottom row of the bottom matrix, right? So multiplying that's like 0 equals 1, right? 0 of like something.
No, this is just a matrix. Don't think of this in terms of
Right.
yeah. Yeah, no, these are two different matrices that give the same row reduced echelon form. So the point is if you and I start with the same matrix, we will get the same row reduced echelon form. But if I give you the row reduced echelon form that says, okay, what matrix did you start with? That's problematic because in fact, all of these. And in fact, this one as well. All of these matrices have this row reduced echelon form. Yes.
So if you just have the steps, you can reverse it though.
Yes, if so, let me clarify. If you have the row reduced echelon form, you can get back to your original matrix, right? So you do your row reduced echelon form to get this, you can use the steps to go back to get this. The problem is there's lots of little forks in the path, so you don't really know where you came from unless you knew your original matrix first. But yes, you can reverse it. Other questions? That clear it up for you all? Okay, so let's show how that these can solve linear systems. So let's actually use row reduced echelon form to solve equations. This is a very important piece of the course right here, is solving linear systems. One can argue that this is really the blood and guts of linear algebra here. And you will see this coming up over and over again, all through the class, this kind of computation we want to do to solve more and more sophisticated problems. So we can have a system. Of linear equations. And create its augmented matrix. Just like we were doing last time, we make that augmented matrix to deal with the equations. The variables correspond to pivot columns or column basic. And the others are called free. So let me give you an example. Let me give you a silly thing. Just to kind of give our feedback on this. So suppose that I have suppose that's my system of linear equation. So it's just one equation, kind of boring, right? Let's form the augmented matrix. This is a 1x3 matrix, 1 row and 3 columns, right? Okay, this is a silly question to ask, perhaps, but what's the row reduced echelon form? Yeah,
Would it just be that?
it's just that. That's exactly right. There aren't any other rows. Your leading entry and your non-zero row is 1. You're good to go. Am I okay with that? Now, there's one pivot column, right? Because there's only one leading entry. And there it is, right? So this is what I mean in this sort of definition over here, that corresponding pivot column here, in this case, y, that's what we call a basic variable, and the other variable x is free. What does that mean? What does it mean to be free? It means anytime. So what if I asked you for the solution to this equation? This is almost going to seem a little silly, but here it is. Notice my free variable can be anything, and my y is 3 minus 2x. And that determines all my solutions, right? So for example, I want x to be 0, so y is 3. I want x to be 1, so y is 1, right? So x has complete freedom. It can be anything I want. But once I choose x, it tells me what y is. Right. Now, so there's one linear system down the tubes. Let's do one that's got a little component to it. Example. Let's look at this system here. X1 minus 2x3 plus x5 is equal to 1. And x2 plus 2x4 is equal to -2. Okay, so let's take a look at this. Let's see, what I got 5 variables here, right? Only 2 equations, 5 variables. 1, 0, -2, 0, 1, 1, 0, 1, 0, 2, 0, -2. There is my augmented matrix, right? Is this in row reduced echelon form? Yeah, it is actually convenient, right? Both of these are 1s, and it's the only non-zero entry in its column, and it's good to go. So, how many pivot columns do I have? I've got 2 pivot elements, 2 pivot columns, and they're actually the first 2 in this particular case, right? So, here's what I get. Here's what I'm kind of gathering so far. And that is X1 and X2 are basic. And X3, X4, X5 are free. So they can tell you how you want. Let me show you how the equation solved. I would just say X3. So what it means, when you've got all the free variables, those free variables are enough information to tell you what everything is. Let's look at these equations here. X1 is equal to 1 minus X1. I'm sorry, plus 2X3 minus X5, and X2 is negative 2 minus 2X4. There's a solution to this equation. I can let X3, X4, X5 be anything. Once I've chosen X3 and X5, it tells me exactly what X1 is. And once I've chosen X4, it tells me exactly what X2 is. So now I've got everything angled. So for example, if I let X3 be 3, X4 be 4, and X5 be 5, the next one would turn out to be whatever this is. 6 minus 5 is 1, that's 1. X1 would be 2. And this would be minus X2 would be minus. Everybody okay? That's how you solve these babies. Let's do one that's not already reduced echelon form. Let's do this one. X1 plus X3 plus 2X4 minus 6X5 is equal to 1. 3X1 plus X2 plus 2X3 plus 7X4 minus 17X5 is equal to 10. X1 plus X2 plus 3X4 minus 4X5 is equal to 9. 4X1 plus X2 plus 3X3 plus 9X4 minus 22X5 is equal to 12. And 5X1 plus 2X2 plus 3X3 plus 12X4 minus 20 something, 27X5 is equal to 10. Hopefully you're already seeing the matrix approach is a lot better, but that was a pain in my butt right there, right? That was really obnoxious. So this is tangled. I think. Let's do this. 1, 2, negative 6. And 1. So that's the first equation. 3, 1, 2, 7, 17. 10. 1, 1, 0. 3 minus 4, 9. 4, 1, 3, 9. Minus 22, 12, and finally 5, 2, 3, 12 minus 27, 20. All right, this looks like death on a hot plate, right? But I think we can get through this. I am going to use this top row. I'm gonna use this one to take everything out. So I'm gonna multiply this by -3 and add it here. So that's going to be 0, 1, minus 1, 1, 1, 7. I'm gonna multiply this by -1 and take this out. 1, 0, 1, 1. Try again, 0, 1, -1. 1, 2, 7. I'm gonna multiply this by -4, take this out, we get 0, 1, -1, 1, 2, 8. And -4, 1, this one. 2, right. -4, 1, -1. 2. Yeah. Oh, I take this, take this. Here, that actually should be the minus. That should be an 8. It's just like one. Finally, -5 here. 0, 2, -2, 2, 3, 15. Now, hopefully, you all notice some cool stuff here. And that is, all of these look kind of similar, don't they? So, 1, 0, 1, 2, -6, 1. I'm going to use this to take out this 0, 1, -1, 1, 1, 7. -1, this can be 0, 0, 0, 1, 1. I'm going to use want to take this out. It's going to be the same thing. And I'm going to multiply this by -2 to take this out. I'm going 0, 0, 0, 1, 8. That's -2. 0, 0, 0, 1, 14, 16. All of a sudden, this is a lot easier. 1, 0, 1, 2, -6, 7, 0, 1, -1, 1, 1, 7. And 0, 0, 0, 0, 1, 1. Because this one, you can take out all the other ones down. It's exactly right. Notice I have 2 rows of 0 on the bottom. That guarantees that I've got 3 variables. And here, actually, is the row we're in section on 4. Well, so I should have, how many pivot columns am I going to have? 3. I'm going to have 1, 2, 3 pivot columns. And so what I get is X1, X2, and X5 are basic. What does X5 equal? 1. 1. And I'll just give you the solution so that you can get to it here. Well, actually, the other equation you get is in row reduced echelon form. What you'll get, the other two equations is this. X1 plus X3 plus 2X4 is equal to 7, and X2 minus X3 plus X4 is equal to 6. So your basic variables, X1 is 7 minus X3 minus 4X4, and X2 is 6 plus X3 minus. And there's the solution. This and X5. Yes.
So even though we have 5 equations and 5 unknowns, we can't figure out 3 of the 2 of them.
What's that now?
Even though we have 5 equations and 5 unknowns, we still can't figure out 2 of them.
Oh, no, no, no. In fact, this actually has infinitely many solutions, right? Because what happens is it's X3 and X4 are 3. So you could, for example, both let X3 and X4 be 0, meaning X1 is 7 and X2 is 6. Or you can let them both be 1 and 7 is 7. Here is a very important point. This system is solvable. So that's the basic question. It's solvable as long as you don't get a row that looks like this. As long as you don't get a row of all zeros and then not 0. See, you're good here. As long as you don't get that in the row reduced echelon form, it's solvable. And you only get one solution if all the variables are basic. If there's even one free variable, there's infinitely many. So, yes,
So that right there is it finished, right? Like we didn't fully.
this is the finish. Oh,
We didn't fully find the review.
no, I didn't. There's only one more step you need. You need to take out this to get the row reduced echelon. Other questions? Yes.
So does that mean that the solution is the coordination of X5 equal 1?
That is correct. X5 must always be 1, right? And X2 and X3, X1 and X2 can vary depending on how X3 and
But those have 3 variables, so that they will be planes, so it would be like
actually, the solution of this, since there are 2 free variables, will be a plane. And we'll discuss that further. That's a different question. Others. All right, y'all have a good one, and we will see you on Monday.